I think you solved the microphone problems. Yes? Do you hear me? Okay. Okay, so thank you so much. Dr. Parker and Dr. Kim perfectly introduced the topic that I'm going to present. And what I'm going to present is the results of a lot of ongoing research that have been done from many clinicians, researchers on basic science, and the histologists, mainly located in Italy, but also spreading all over the world. We have connection with South Africa and Brazil and North America, and of course with South Korea, with all the researchers from Megagen. So this is a very brief presentation of what we are doing and what we have done in the last 3 years on this topic. And before going deeply in the topic, I just want to just a brief summary of what we may do when we have to manage the regenerative and reconstructive procedure. When we have to choose the material, we know that we can choose autogenous bone, we can use homologous bone, we can use heterologous bone, and finally we can also use synthetic biomaterials. So when we are in front of this kind of procedure, we have to choose and which is the right material to use in this kind of procedure. And we know that is a big problem because over 2 million bone graft procedures are performed annually worldwide, and in 90% of this procedure, autogenous and homologous and heterologous bone is used, while only actually 10% of synthetic biomaterial is used. And of course, we know that autogenous bone is the gold standard, is still the gold standard because it has cells, so is osteoconductivity, is inorganic matrix, so it has osteoconductivity, and it has also growth factor, so it makes osteopromotion. But we know that autogenous bone has some problem. We have a sort of morbidity at donor site. The surgery is not real easy, and so you need some skill to do this. And also we have some adverse event complications. And when we speak about the homologous and heterologous bone, we have a lot of products on the market. And we know that what we may expect from this kind of product is only the osteoconductivity, because of course they don't have any cells and growth factor. So, but when we speak about all these kind of materials, we know that there are some risk of disease transmission, some risk of HIV transmission, and why not risk of prion disease transmission. And we see what is in the literature. Risk of disease transmission, we know that there are a lot of techniques to decrease this kind of risk, but according to the literature, none of this treatment may guarantee absolute sterility, we know. And when we come to risk on HIV transmission, there are some papers from the literature for more than 20 years that says that it is possible with this kind of material, a sort of the transmission of HIV. And when we go to the prion disease transmission, you know, this is a very recently review of the literature in 2011, and the conclusion of this article is that proteins, including collagens, were detected in some organic and bovine bone substitute, including pseudoplast and the efficacy of BSA prion inactivation has not been proven based on current literature review, and also the systematic review indicates that bovine-derived graft biomaterial may carry a risk of BSA prion transmission. Just to know what is going on is coming from the recent literature. And there are also a sort of contraindication, I wouldn't say contraindication, but set a warning about this kind of procedure. So what we strongly believe that the future is these synthetic biomaterials, because they are safe, because it is possible to customize with the new technologies. You can prepare a synthetic biomaterial completely customized in ultrastructure and in shape, and also because these synthetic biomaterials are excellent carriers for tissue engineering, scaffold for tissue engineering. That's our philosophy on which we are working since more than 10 years. And about this material, calcium phosphate ceramics and porous HA is the most studied one, more than 30 years of research, more than 2,000 publications. And these are some of the publications from our group starting more than 30 years ago. And again, this is some other of the publication that our group have published in the last 20 years. So what is the ideal synthetic scaffold? The ideal synthetic scaffold should have a defined by biomimetic micro and macro structure, and should have the possibility to be customized in shape. This is the future on which we are working and on which we have already done some things that I will show immediately. So when we speak about the ideal synthetic scaffold, we know that the scaffold has to have the porosity, a sort of porosity, a sort of interconnected open pores, tunnels, concavity. So in a few words, it has to have a specific 3D architecture. And we know that this architecture is absolutely necessary, because we have to have in this interconnected close porosity fibrovascular tissue, the osteoid tissue, and mineralized tissue. And we also know that this has to have must have a special geometry, because a special geometry we know is important for the osteoblast and for the new formation. We know that a special geometry has been tested since 20 years ago by the group of Ripamonti in South Africa. And this kind of geometry is perfect for the new osteoblasts. And this kind of geometry, just by itself, by its shape, is a good induction also in extraskeletal sites. So we have to prepare a synthetic biomaterial, completely synthetic, in mimicking the geometry of the natural bone. And now with the new technology it's possible to do a biomaterial like this. And also we have to make a sort of chemical biomimesis. So the structure, the ions that are on the natural bone have to be reproduced in the synthetic scaffold. And going deep in the topic we are of this morning, we have to. I want to show you what our experience on custom-made biomaterial reconstruction. We have seen perfectly from Dr. Kim what is the sequence, and I will try to show you some of the cases we have already done using different software. We have seen this morning from Dr. Kim that the R2 software is really much better than the one I'm going to show, but you have to think that these are cases we have treated between 2009 and 2013. So we use a different software according to what we managed at that time. So the concept is the same. We have a TC scan. We can do a virtual scaffold of the defect. We can go inside the mat and put the scaffold on, and we can pass from this kind of a very thin ridge to this ridge just with a very easy surgery, because the shape of the block is exactly the shape of the defect. And after this, we can go on putting in our implant. And again, this is another defect, vertical and horizontal defect. We treated a very small defect at the very beginning, and now we are going to a little bit larger defect, but you know the most large is the defect, the most difficult is the case, the most you have the possibility to have failure. And this is the virtual treatment of the defect. And from this spine, with a STL file, we can go straight to the device which prepare our block just by a milling process, and we can, the device perfectly mill the block of biomaterial according to the shape straight from the file that received from the virtual planning, and we receive this piece and with a sort of frame. And what you have to do is just to go hand them out, open a flap, put this in. In this case, you have to use a screw, and this is after, and this is the defect as it was, and you can go on with the implant up to the end. And again, this is another case. It's a very challenged defect because it's completely is a defect that is very difficult to treat with the regenerative procedure. What you do is prepare the virtual scaffold again. You receive the piece on the right side of the screen. You see a film of another case very similar to this, just to see the procedure. You receive the block. The block fit perfectly. You just have to do very little relining. And this is what you find 6 months later, the perfect integration of the block. As you can see on this side, you put the block, just one screw, and you can prepare on the block, on the virtual block, the hole for the insertion of the screw. And this is the histology at the time when we come back 6 months later to put the implants, and this is the final treatment with the implant and the crown. And so these are some of the papers we have published. I have not the time to go in detail with these articles, but you have all the reference, and if you want, this is the first article we have published using this technique with a bone block inside the sinus. And this is the what you can do. You can also do a stent to open the window on the lateral side of the sinus exactly of the shape of the block you have to put in. So when you go in on the theater, you can prepare a window of the perfect size of the block you have to put in. And so what you receive is this kind of block, and this is the virtual treatment, and this is the block. You go on, and this is the block inside. This is the, the stent. Through the stent, you can open this window. After opening the window, the block passes through the window perfectly because you have everything is set before surgery, and you can go in like this. And this is the block inside the sinus. And this is the final, after 6 months, again, you have to wait. After 6 months, you can put in implant and then the tooth. So we have to go very fast because we do not have time to do, okay, on the right side of the screen, you can see some of the step of this procedure. At the end, you just have to reline a little bit the block, and you close the flap, and everything is done. And in many situations like this, we have done around 10 cases. You don't need any screw to fix the blocks because it's so stable you don't need anything else. And this is what you can find after the integration of the implant. And so this is another article we have published very recently, 2013 in May, in which we treated it, just a case report in which we treat posterior defect, bilateral posterior defect. The situation is the same. The virtual place like this. This is before, and this is after, and these are the implant inside. And what is happening? Okay. And this is the one of the ongoing publication. No, is it still published? It's already published online, but this is in press on the paper, and it will appear on the Journal of Oral Implantology. And this is the first prospective study we have done, of course, only on 10 cases, as they told before. This kind of procedure is at the very beginning, so we treated very not so many cases, but anyhow we are trying. We think we understand what we have done in the future to better perform this procedure. So, what are the future development of the procedure? First, the additive manufacture process. So, we are going to towards a printing process of production of this kind of block instead of milling. And the other thing on which we are working is custom-made biomaterials as a carrier for growth factor and stem cells. So, speaking about additive manufacture process, we know that the process actually is this, as they already showed you, CT scan, CT DICOM. You put the information in the software. In the software you can design a virtual block. The file straight goes to the device, and the device produces this kind of scaffold. What we are doing now, and we have prepared the first one, is this. So the different way is a 3D laser printing, and we can straight prepare a printed, customized biomaterial. And this is the first piece we have produced with a file that came very kindly from Korea last week, and we received very recently this kind of block. So when we speak about custom biomaterials carrier from growth factor, because we know that the scaffold in which you can add stem cells, so BMPs, is the first step for tissue engineering. So we may do everything with this thing. And we have a lot of examples from the orthopedic field. These are some of the use of this kind of porous. And this is these are some of the works on animals with ceramic scaffold and stem cells, and in human, and in many of these studies we are involved. And these are some of the recent publication on this topic from the group. And going deeply, this is the most recently ongoing study in which we have compared this new porous HA. This is completely predefined. It's a very new HA in which we may define the ultrastructure and shape, and this new porous HA with amniotic cells added in sheep. And these are the early results we have done. At 45 days histological analysis, and at 8 days histological and morphometric and micro-CT analysis. And what the results are this. At the control sites at 45 days, good bone filling of the scaffold porosity, and it is possible to see cell and vessel in the new growing bone. So this material by itself lead the cells to go inside and start to grow. But what is amazing are the results when you add the cells, because all the porosity are completely filled, as you can see here, of new bone. The fibrin matrix is rich in cell and vessel, and what is very nice is the ossification fronts are in direct contact with the scaffold. So the scaffolds, the behavior is something that is vital instead of being just a scaffold to lead the cells. And when, again, the immunofluorescence, the stem cells in red and the new osteoblasts are around the vessel are very evident, just to stress the concept I have just told. And these are some of the works we published on these things. There are 2 papers already published, and there is a 3rd one that is going to be published on the Journal of Oral Implantology. And also, this one is the most important one on +1 that is a very huge impact factor. And another field in which we are looking is the dental pulp as a source of stem cells, because the dental pulp has a high ratio stem cells number for tissue volume. There is a low morbidity because you can find inside the mouth, and has an easy surgical access. And also on this, we have done the group in the University of Naples have some publication starting many times ago. And what happened? Okay, and so we have some human clinical studies in progress with porous HA and BMPBs, and porous HA and dental pulp stem cells. So, conclusion, and before to conclude, I just take 30 seconds to thank so much for the invitation. It's Dr. Parker and the Megagen group with whom now we are in very close contact since a couple of years. It's really an honor for me to stay here. And also I would to thank the Thailand. That is a fantastic place. This is my 2nd time here, and it's really amazing how the population of this country are so, their kindness there it's really fantastic to be here. And in the last minute I have, I would wish to conclude just to set what a very, in a fast run I presented to you. We have seen that the organic bone substances seem not to be completely safe, and the synthetic biomaterial might be the new frontier of bone regeneration. And porous HA, we have seen, is the most studied biomaterial, more than 30 years. And with the new technology, a new Custommade porous HA-derived biomaterial is ready to be produced with these new technologies. And this new biomaterial is customizable in microstructure and shape, and finally, it is ready to be produced by sending an STL5 to a milling device, and very soon it will be produced straight by printing process, and it is an excellent carrier for stem cells and BMCs for future application. So this is the conclusion of my presentation. If you want some other information, please do not hesitate to contact us at this mail. And thank you very much for your attention.
Thank you, Professor. Thank you.